Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at first order reactions. And no, we're not talking about Star Wars today. So one of the biggest types of reactions that we tend to see in terms of kinetics is first order reactions. So these are reactions where I go from A to B, and it will actually depend upon the concentration of the reactant. So this is often represented as being to the first power, but often shorthanded as with the rate law of rate just equals the rate constant times the concentration. And one of the big noticeable things about this is that what we are really seeing here is that the rate has a concentration dependence. And as a result, we tend to see that the reaction goes faster at high concentrations and slower at low concentrations. And again, we can go ahead and see this with how that change occurs. As the concentration of A goes up, so will the rate at which A is consumed. And this ends up producing some rather fun rate laws. As again, we see that this concentration goes down swiftly at the beginning and then slowly levels off. And one of the big tricks of this is trying to find a good way to determine the concentration at any given point in time. So what we can do is use our original rate law and perform some math magic, also known as calculus. So what we can do here is say that, all right, my rate is my rate can be given as the rate constant with times the change in time. And then we're going to go ahead and collect all of our concentrations over here on the left. So we have a negative change in concentration of A over A. And then math magic, also known as calculus, same as before. We're integrating from 0 to T on the left and initial to final concentrations on the right. So when we do this, a fun thing happens when you try and take the integral of 1 over a variable. A natural log pops out. So on the left-hand side, it's the same thing we've seen before. It's just KT. Again, if you have different stoichiometry, the stoichiometric coefficient often shows up here because you're just consuming that A faster. However, over here on the left-hand side, we get some fun because now we have the natural log of our final concentration over our initial concentration. However, due to the nature of logs, you can go ahead and remove a denominator by subtracting out the log of that value. However, since we have a negative log out here, this gives us the negative log of our final concentration plus the log of our initial. Then we can go ahead and rearrange things, move our log over to this side and our KT over to the other side. And what we have is the natural log of your concentration of whatever reactant you have at time t can be given by the negative of the rate constant times time t plus that the natural log of that initial concentration. A good way to look at this is that our initial concentration gives us where we start, and then we're going to be taking away from that. We're going to be taking away more concentration as the more time goes on. And this basic equation is referred to as the first order integrated rate law. However, as you may notice here, the graph of first order reactions isn't exactly the most fun thing, as it is very hard to try and figure out what your rate constant is just from this reaction. So a very natural tendency is to find a way to turn this into a straight line. And it turns out we actually have the equation with the integrated rate law. We can go ahead and plot the natural log of our concentration versus time. And this should give us a nice straight line just by switching our units on our left axis. Now, one of the really cool features about this is that since time is our x-axis, it means that everything before it is the slope. So the rate constant is just equal to the negative of the slope of the reaction. So by simply plotting this behavior, ta-da, we can get the rate constant and confirm that it's first order. An extra benefit is that you can often, if you know the concentration and the time since the reaction started, figure out what the initial concentration is. And this is actually used in a lot of devices, such as breathalyzers, who look at the oxidation of alcohol and using a first order reaction by measuring how the measuring the color of the reaction and the amount of time since the two reagents were mixed, you can back out that initial concentration of alcohol. However, we can also use this relationship to derive a half-life for a first order reaction. And again, note that this will be different than a zero order. So in this case, we can go ahead and start with a derived form of our first order integrated rate law, where we now have KT equals the negative natural log of final over initial concentration. And then we say, haha, if I've let half of the reactant consume, I can go ahead and replace T with my half-life. And I know that my final concentration is half of my initial. By plugging that in, we now have on the right-hand side, the negative natural log of our initial concentration divided by 2. So that puts that 2 in the denominator over the initial concentration. Well, now our initial concentrations cancel out, and it's quite pretty because we now have negative natural log of 1/2. Now, a fun feature of natural logs is that a negative natural log is the same as the inverse of whatever you're taking the natural log of. So thus, negative natural log of 1/2 is the same as natural log of 2, which means that that KT equals natural log of 2. So thus, we can get our half-life simply as the natural log of 2 divided by the rate constant. And this is very different from what we saw before, because the half-life for first order reaction won't change with time. It is very constant. Only thing it changes upon is the rate of the reaction. So as long as that doesn't change, your half-life can be quite predictable. And this is used in a lot of applications, such as radio dating, which we'll be talking about a lot more next chapter. So we can go ahead and look at this half-life behavior if we look at the decomposition of something called diT-butyl peroxide, or DTB, which breaks apart into acetone and ethane. So this reaction essentially sees a quick decrease in the concentration, and then a slower decrease, and then slows down as time goes on. But note that each time every 80 minutes, the concentration of DTB goes down by half. And the reason why is that the decrease in the rate is matched with the decrease in the concentration. So these two effects essentially cancel out. So every 80 minutes, we have exactly half as much of my reactant. By the time you get to 240 minutes, you've had 3 half-lives take place, and you end with 1/8 of the original amount. And this can be used for a lot of dating. If you know what your initial concentration should have been and what your concentration currently is, you can figure out how long the reaction has taken place. And as I said previously, first order reactions are really one of the most common types of reactions. They take place in all of our radioactive decay reactions that we'll talk a lot more about next chapter, but also in a lot of reactions of individual materials, metabolism, decomposition reactions, acid reactions. Almost all of these are first order reactions. And so this is a very important feature when trying to examine how reactions take place and how quickly they take place. So next time, we'll go a little bit more complicated as we go up to second order reactions. Until then, take care.